You probably use a smartphone every single day, but inside that sleek glass and metal shell, the electronics actually function a lot like the pipes and valves under your kitchen sink. If you crack open any electronic device, you'll see a crowded landscape of tiny parts. Those little cylindrical towers and brightly colored ceramic discs, those are called capacitors. While they look complex, inside the design is surprisingly simple. A capacitor is essentially a sandwich of two flat metal plates. The strict rule: they can never physically touch. A solid material, called a dielectric, is wedged between them, blocking any connection. This creates an interesting puzzle. If the plates are completely blocked by an insulator, how does electricity actually travel through the component? The answer is that it doesn't. A capacitor doesn't let electricity flow through. It captures it for later. To see exactly how it pulls this off, we need to think about water. Imagine the invisible flow of electricity through a wire exactly as water flowing rapidly through a clear pipe. In this system, your power source, like a battery, acts as a mechanical water pump. It constantly pushes the fluid forward, keeping everything moving in a continuous loop. Now, let's install a capacitor into this pipeline. Picture it as a wide water tank right in the middle of the flow. But inside this tank, there's a thick, flexible rubber membrane dividing it perfectly in half. As the pump forces water into the left side of the tank, it pushes against that barrier. It stretches the rubber outward. As the membrane bows to the right, it forces an equal amount of water out of the right side of the tank and down the pipe. Notice that not a single drop of water actually passes through that rubber barrier. Instead, the stretched membrane is now holding back intense physical pressure. That flexed piece of rubber wants to snap back to its original shape. In the exact same way, a capacitor builds up and holds electrical pressure, keeping that energy ready to be used on demand. If we zoom in closely on the actual metal plates of a capacitor, we can see this exact process happening with electrical charge. When you connect a battery, it acts like our pump. It forces negatively charged electrons down the wire, causing them to pile up densely on the first metal plate. Because the solid insulating material blocks their path, these electrons have nowhere to go. They crowd together and get stuck. This crowding creates intense electrical pressure, which we measure as voltage. Electrons naturally repel each other, so this massive crowd of negative charge on the first plate pushes away the electrons sitting on the opposite plate. As those electrons flee down the wire, they leave behind a net positive charge. The capacity to store these separated charges is measured in a unit called the farad, named after the 19th century scientist Michael Faraday, who helped figure out how these forces work. When the plates are completely full and the charges are gridlocked, the capacitor is fully charged. It has successfully stored electrical energy without a single electron ever crossing the gap. This raises an interesting question. If the electrons are just sitting stationary on those metal plates, where exactly is the energy hiding? Because opposite charges attract, the packed negative electrons on one side are desperately trying to reach the positive space. There is an intense, invisible attraction pulling them toward each other. We call this zone of tension the electric field. It is the exact electrical equivalent of that stretched rubber membrane in our water tank. If you completely remove the battery from the circuit, the capacitor doesn't lose its charge. It holds on to that tension indefinitely, waiting for a new path to open up. The energy isn't moving through the wires. It is locked inside that field, held tight like a coiled spring, just waiting for the chance to snap back. Batteries create all of their power through chemical reactions, meaning they dispense their energy slowly and steadily over time. Because a capacitor stores its energy as pure physical tension, it doesn't have to wait for a slow chemical process. It is able to unleash its entire payload of energy in just a tiny fraction of a second. This instant release is incredibly useful. It's exactly how medical defibrillators work, using heavy-duty capacitors to deliver a massive, life-saving surge of power all at once. This graph shows how a capacitor handles its other main job, acting as an electrical shock absorber. When the power coming from a wall outlet fluctuates and gets choppy, it travels directly into the capacitor. As the power dips, the capacitor instantly releases just enough of its stored energy to fill in the gaps. This ensures the delicate electronics inside your phone or computer receive a perfectly smooth, steady flow of electricity without flickering or resetting. Whether they are dumping a massive bucket of energy for a sudden flash or quietly absorbing the bumps in an electrical current, capacitors do the quiet, essential work of keeping our technology running smoothly.